This is ELC111, Introduction to Electricity, and this presentation is on amplifiers. Now, the symbol for an amplifier is shown in Figure 1. It's just a triangle with V in on the left and V out on the right. By convention, electronic schematics are always drawn with the input on the left and the outputs on the right. The schematic symbol in Figure 1 shows what's called a single-ended input amplifier. And this is what we obtained with the transistor amplifier Figure 2 that we discussed in the previous presentation. There is just 1 point for the input signal and 1 point for the output signal. And as we talked about in the prior presentation or the previous presentation, the key metric for discussion of amplifiers is the gain, the voltage gain. Gain symbolized with the capital letter A and the subscript V denotes voltage gain. And mathematically, voltage gain is V out divided by V in. For example, if an amplifier has an input voltage of 10 millivolts and an output voltage of 5 volts, then the voltage gain is 500. Another example is that if we have an input voltage of 100 microvolts and a voltage gain of 5,000, we can calculate the output voltage by rearranging the equation and solve for V out, where V out would equal 500 millivolts. Now, an issue that comes along with some amplifiers is what happens if the voltage gain is too large or if the input signal is too large. So in Figure 3, we see an example of an input signal and a clipped output signal. So you can see in Figure 3 that at this point right here, the positive peak of the output signal is clipped off, and of course also the negative peak of the output signal is clipped off. And this is what we refer to as a distorted signal. And distortion is the case when the output signal is not an exact reproduction of the input signal. Now, with EEG measurements, from what I've read, the input signal can range anywhere from 20 millivolts to 140 millivolts. And it may be a case that the gain is such that a 20 millivolt signal will not be clipped. However, a 140 millivolt signal might be clipped and distorted. So it's not uncommon, or it's the case where our amplifiers need to have some means of controlling the gain so that we do not clip or distort the output signal of the amplifier. Now, with amplifiers, we always have to have some source of power, and that's to power the transistors, and some path to ground, as we see in Figure 4. VCC is denoted as the positive voltage connection for the amplifier, and of course the ground is simply ground. Now, understand that the output of this amplifier can never be larger than VCC, and the output can never be smaller than ground. So this might lead to a case again where we could have clipping and distortion in our output signal if the gain of the amplifier is such that we try to make the output larger than VCC. Now, amplifiers also have some value of input impedance as shown in Figure 5. And the input impedance, remember, impedance symbolized with the letter Z, which is the opposition to alternating current. Zn is simply the opposition to whatever signal is applied at Vn. Now let's look at the effects of Vn, or the impact of Zn, on the performance of an amplifier. So in figure 6, we see a source voltage, an AC signal, Vs, connected to the input of an amplifier. And as we discussed many weeks ago, all voltage sources have some internal resistance. Doesn't matter what this voltage source is, whether it's a battery or a sensor, an EEG lead, it doesn't matter what it is. All sources of voltage have some internal resistance. And referring to the circuit of figure 6, see that R internal and Zn make a series voltage divider. That when Vs supplies some current flowing into the amplifier, there'll be some voltage dropped across R internal. So the input to the amplifier is not equal to V source, because there's some voltage drop before it gets to Vn. So mathematically, we can calculate Vn using the voltage divider formula. Vn equals V source times Zn divided by the sum of R internal and Zn. So for the values given, a source voltage of 10 millivolts, an input impedance of 1 kiloohm, and an R internal value of 1 kiloohm, note that we only have 5 millivolts applied to Vn. Because we've got 5 millivolts dropped across R internal, we therefore only have 5 millivolts left to be amplified from the total source voltage over here, which was 10 millivolts. So for our amplifier, we really need to have a large value of input impedance to improve the performance of the amplifier. So we look in figure 6, an example, again, an amplifier with a signal source, Vs, connected to R internal and an input impedance to the amplifier. Again, R internal and Zn comprise a series voltage divider. But for this example, again, we have an input voltage of 10 millivolts. We have an internal resistance of 1 kiloohm, but in this case, the input impedance of the amplifier is 1 megohm. Now, I go through or show the equation to calculate Vn, again using the voltage divider, and we yield an input voltage to the amplifier of 9.99 volts. And the reason this happens is because of the 1 meg resistor over here for Zn, the amount of current that flows into the amplifier, I, is going to be really small, because we've got 10 millivolts divided by 1.001 megohms. So this current is almost zero. Therefore, the voltage dropped across R internal is going to be approaching 0 volts. And the voltage applied to Vn is going to be approaching 10 millivolts. Mathematically, we end up with 9.99 millivolts to be amplified. Now, we really need or want for our amplifiers to have a situation where the input impedance is at least 100 times greater than the internal resistance of the voltage source. And the reason again for that is we don't want voltage dropped across R internal. We want this voltage to be as small as possible. And as long as we satisfy this 100-to-1 ratio, we can assume the input impedance is high enough or large enough to not create a voltage drop inside the voltage source. Now, Figure 7 shows us the schematic symbol for a differential amplifier. Note with the circuit of Figure 7, we have two inputs. One's labeled plus and one's labeled minus. The plus input is called the non-inverting input, and the minus input is called the inverting input. And the differential amplifier amplifies the difference between these two inputs, the non-inverting input and the inverting input. Mathematically, V out equals the non-inverting input minus the inverting input times some value of gain. Excuse me. Now understand that the differential amplifier, just like the single-ended input amplifier, has some input impedance, but with this case the input impedance exists between the non-inverting and the inverting inputs. The voltage that's actually amplified is the difference between these two voltages. Again, depending upon the value of Zn, when current flows through the circuit from Vs to ground, there'll be some voltage drop across our internal, and it's Vs minus this voltage drop that's actually amplified. So like with our single-ended input amplifier, we want Zn to be at least 100 times greater than R internal to reduce the voltage drop across R internal. We want Vn to be as close to Vs as possible. Now, one of the features for the differential amplifier is its ability to reject what is called a common mode input signal. So referring to the circuit of Figure 9, note we have an AC signal called VCM, or labeled VCM, and this is the common mode input signal. And this common mode input signal is applied to both the non-inverting and the inverting input terminals. Now, ideally, the output would be 0 volts, because mathematically V out equals V plus minus V minus the voltage at the non-inverting input minus the voltage at the inverting input times some value of voltage gain. And if we have the same voltage applied to both the non-inverting and inverting input terminals, the output voltage will be, or should be, 0. However, because of variations in the current gain of the transistors in this amplifier, then our output will not be the ideal value of 0 volts. It'll be some other value. Common mode rejection ratio tells us how much this common voltage is rejected. The common mode rejection ratio is typically expressed in decibels. And a typical value for a differential amplifier would be a common mode rejection value of 100 decibels. Now, to change 100 decibels back to a ratio, we would have to take 10 raised to the 100 divided by 20 power. This is going back to our conversations on expressing gain or loss in decibels, which would give us a common mode rejection ratio of 100,000. So for example, if my common mode input voltage is 100 millivolts, and we're given that the common mode rejection ratio of the amplifier is 100 dB, then our output common mode voltage would only be 1 microvolt. And of course, this mathematically is 100 millivolts divided by 100,000 to give us 1 microvolt. So if I apply 100 millivolts of a 100 millivolt signal to both of the input terminals, the signal at the output will only be 1 microvolt. Now with our differential amplifier, what we want to do is to be able to amplify some input voltage, some source voltage, shown in figure 10 as Vs, and also be able to reject the common mode signal that would appear in our system. Now remember, the output of our differential amplifier, V out equals V plus minus V minus, the non-inverting input voltage minus the inverting input voltage times voltage gain. Now if we look at the circuit of figure 10, note that to the non-inverting input terminal we have V source plus VCM, V common mode. Series voltage sources are additive. However, to the inverting input terminal we only have VCM. So mathematically my output should be the sum of these two voltages, Vs plus VCM minus VCM times AV. So the source voltage, Vs, that's my input signal, is amplified times AV. However, the common mode voltage is rejected by the common mode rejection ratio, as we saw in the last example. Now, one of the situations with our amplifiers is that the differential amplifier itself rejects any common mode voltage, but any value of voltage gain that we have with the amplifier also amplifies both the input voltage Vs and the common mode voltage. So the gain of the amplifier actually reduces the common mode rejection ratio, or the common mode rejection capability of the amplifier. Again, if we amplify both Vs and VCM, then VCM will not be reduced by the value of CMRR. So when we talk about a differential amplifier that has some gain associated with it, we have to reduce the common mode rejection ratio by the value of voltage gain, and we get a new term that I call the common mode rejection of the amplifier. So CMR equals CMRR divided by the voltage gain. And of course we can calculate the common mode output by taking the common mode input divided by the common mode rejection value. So for example, we have a source voltage of 1 millivolt. So let's put that right